Hi everyone. Today we will examine another example of design of starting from the model of a reference system, as we saw in the previous example applied to the chemical reactor case, and then it was used for the synthesis of intelligent controllers, and in particular a neural network that was applied to a model. Well, it was not really a model in the case of the reactor, because it was just the data. It was represented just by the data. But in this case, we have a realistic model of a directional antenna, which is described by a nonlinear process. So even if the nonlinearity, as we will see in the simulator, is quite limited to, is quite simple because it's limited to a sinusoidal function. But in any case, it represents a nonlinear and a realistic description of a quite known and quite established model. And then it can be useful in order to learning the procedure that is applied for obtaining these specific controllers. So let's start with starting from the file. So we have a complete file, which is a zipped file, which contains all the data and the solutions and the files that are used for this specific problem. So let's start with the bind download. So the name of this file is antenna problem data files .zip, and we have it here in this folder. And then we'll start with you will find the several folders that contain the step-by-step the designs that are proposed in this lecture. So let's start with the first step, as we saw in the previous case, of the linear identification. So even if it's not really useful, I mean directly useful for the design of a controller, but it represents a basic and an introduction for understanding, for example, the delays that are that need to be considered for the description of the model of this system, and then the design of the controller. So let's start with the linear identification, and we will see the several files. So let's start with the first file, which is represented by the file. So this is the simulator that is used for this application. And then in the specific here, we have the nonlinear model. Let me check first, because okay, we need to change the folder so you can see also the picture of, well, it's not really important, but in any case you can, so we can we have gen data ident, so the basic file that is used for generating the data. And just a second. Okay, now you can see also the picture. So we have in this case you have the reference here, and you have the reference which represent the input, and then you have the antenna nonlinear model. We can check it, as I saw already, as already mentioned. And so you have here, you can recognize that you have the main control variable is the angle, and after an integration you have the velocity, the angular velocity, and of course is represented by the drag factor. So it means, in fact, that the moving antenna is subjected by a drag of 2, which depends on the velocity, the angular speed, and then we have the dependence of the function of the position, which affects of course, the weight, the gravity, the weight of the antenna, and the main input, so the forcing input, that is represented by the force that, for example, can be generated by an electric DC motor, for example, depending on the specific application. So there are some other variables can be obtained, but they are not used in this case. For example, the velocity and the acceleration, that maybe they can be used for more complicated controller design, but they are not used here. So we have the input sensor with the noise. It's important because we have a reference, and then so the position acquired by an output sensor, and you can see here that the output is measured by means of an output sensor which introduced some noise. So this simulator is also introducing some realistic effect due to the, for example, these electrical or sensor or electrical devices that are used for measuring the position and the force generated by for example, the torque probe that is used for measuring the force generated by the DC motor. And then we have especially for the purpose of the linear identification, we have the generation of these two vectors u and y, and a number of data depending on the sampling time. And we can see that we have another file which is init model, and here you can see it's just provided for your interest, but we have that the linearized model is described by a non-purely dynamic model in the state space. So when you consider the linearized model, you can obtain a second order, and the suggested sampling time is 0.05 seconds. And so this is well, they are not really used, this at least the sampling time, but you have at least the matrices that can be useful for understanding the dynamics of the system. And then we have a second file that is used for which is called data for identification, and you can see that is the preparation for the linear identification. So after you have generated the data u and y, you make a partition into two sets, the estimation data and the validation data, that they will be used in the system identification toolbox. So let's run this simulation in order to get these two vectors, two sets of vectors. And I don't know if, of course, I didn't run the simulation, and of course now we have the data, and we can see here that we have in this case, for example, this is the input and the output which is obtained. So here are the signals, and you can see them here in case we can be interested, we can add here another, just to check how they are modified by the noise. So we can put here a multiplexer, and then we can see, or we can have a double, like in this case. Better, we can have two. Okay, now let's run again. And okay, and you can see here how they are modified. The two, this is the reference, and here you can see here the output. Then let's now we have generated the data, and then we can run the this file that is used for data for ident. Okay, now we can run it, and we can see that in the workspace we have U and about 3,000 data for the estimation and the validation. So let's call ident, which is opens the graphical user interface. And if you recognize, so quite quickly we can import the data, in particular time domain data. So is UE and YE, which represent the estimation data. I call them data estimation starting from 0, and the sample time is the S. So import. Okay. And then we can upload the validation data, which are called YV and UV, called data V validation, and we start in time. So we have two close, okay. And then now we use data estimation are used, so are drag and drop in the working data, and the validation data are put here. So we have, and we can inspect them, and as you can see here, we have two sequences of data. And so let's start with the, we are not going to process them, so we can leave it them and as they are, and then we can, for example, estimating let's try with a state space model first, and as we saw at the beginning, and just to understand which kind of model can be obtained in order to consider a state space model. So we can, of course, we have to use a discrete time, and we can select observability canonical as a specific, and we can have pick the best value in the range. So as you can see, notice now you have a value of 2. So in fact is suggesting that the model is in fact of second 2, as it was provided by the linearized model. So we can estimate it, and then we can consider it, and then close this. So we have the model output, and we can see that is quite well. The simulation is quite, as you notice, is quite accurate, because you have 87.39%, and if you consider, for example, a 5-step ahead predicted values is 84, And if you consider one step ahead prediction is 85, so it's quite good, this model, because as if we use this model as a predictor, we have 85.63 or as a best fit. And if you are considering it as a simulator, is even better, because if you notice, it's quite good. So it means that a second order can be considered a quite accurate approximation. And if you, as we saw, we can estimate a polynomial model. And for example, if you check the order selection, and for example, estimate, also focus, by focusing, since we will use these models as in simulation, because they are normally exploited for the controller design. So we select the focus on the simulation, and then we can estimate. And you can see here that according to the minimum description length choice in green, it would suggest a number of delays, 10, 3 delays on the input, and 3 delays with on the input with respect to the output. According to a Kaiken information criterion, which is in blue, will increase the NB with 3 delays between the input and the output. And according to the best fit is considering the maximum of the delay. So I don't feel that this suggestion is quite true, because is quite high the suggested model. So instead we can perhaps, you can see here that the misfit is not really improving, because when you can see that is always about 2, so even if is almost constant when you are moving to, and you have an abrupt change between 2, and even if you are considering, so we can for example select the model and order. Let's try with 4, 1. Let's try estimate this kind of model just to see. And let's see how this model is describing. And in fact, you can see that it's quite, as a simulator, is quite high. So we have 74%, which is quite high with a model of 4 order. And if we move it here just to estimate a polynomial model, for example, of a second order, just to understand, let's see a second order, and in order to compare it, a third order, 3, estimate, and close. And so we can see that you can see that we have a second, third, we have 83%, and 74 using a fourth order. And then we can see, by considering one step ahead prediction, it seems that again the model of order 3 seems quite good, and the second, so you have the fourth, the second, and the third, and in simulation again you have a 2 or 4, and the third is 83. So it's quite high, because if you compare, for example, you have that state-space model is about 87, so is very close to 80 to the Rx of order 3. Let's try, for example, another last check, for example, a polynomial model of order, again, in order to, and let's try it with the fifth order. In order to understand, and we have the output. So, and in fact it's 79. So it seems that the best is the of course the space model, and you have the Rx. So I think we can consider for example the ARX of order 3. And I tried also, I will show you, the ARX of order 4, and we can keep this model, and for example compare the order 3 to the workspace, because by leaving the state space model, and so the model output, we can see that, so the best one is the order 3, and so we may consider the model of order 3 and as a best model for just for considering the linear approximation, so to the workspace. And of course we can consider also the model residuals, but if you notice the model, so the model of order, none of the models is really that none of the model is not really describing of course the system is not linear, so it's quite difficult to find a system. Also if we deselect and we consider only the state space model, also in this case you can see here that the autocorrelation and the cross-correlation functions are not are not limited, are not in the inside the values, and then it means that perhaps of course the model is not really valid, but so we can go in the then in order to validate them, so we can save them, so you can so you will find everything here, so we can close it, and then we can go open the file that I used for I call it linear ident model validation, and then we can we can see if well, I tried with the model of order 4, and just a second. Okay. And we can try with the validation. Let me check if I can. Okay, RX331. So I renamed this, so it's model validation X441. For the case of order, we can check later X, and then save it, save as another for the, in particular for the model RX331. Okay, so we can rename it RX331 model, and here we can include rx 331. Of course, this okay. Okay, and then you can see here that I enclosed the variance accounted for and the comparison of the error, the estimation error, and then we can I included also this recursively square estimator block, and then now I modified in order to consider the model order. So in this case, modifying it in order to consider, so the modify, because I tried first with, okay, six parameters, and then we can reconnect it in order to, so we have okay, so we have these regressors, and then we can reconnect also for the output. Okay, so now we have, of course, I connect also the regressor, and I put six as number of parameters and a forgetting factor of 0.97. And let's try to validate it, run. Let's try to, is this working? Let me check if we have some good results. We have found that you can see here that it seems quite, of course, it's not perfectly well. The error you can see here that is quite small. In fact, we obtain a variance accounted for of 95.28%, and if you consider also the time varying parameters, you have 95%. So it means that a model of order ARX 331 is quite good in order to provide a description, and we can see later and we take these considerations in mind, because for example, when we are designing the delays that are for example considered in the neural network, so this can be a suggestion for how many regressors or which kind of regressors we need to design for our model. So is something that can be considered, and if you consider also here that the error is quite small, and the tracking error is almost, as we can see that the reference in yellow and the predicted output in blue is quite, of course, is trying to follow our system. So it's something that we may consider. So it's something that we need to. So I can check it, and you can consider for as an experiment for understanding some preliminary knowledge of the model. And then we have also the, of course, the model of order 4. That is something that I tried. I need another experiment, so I save it, and I can save it for you. So save data 0. Data I can ARX 331, so you are able to, and then load. I can upload the other, and now save RX 441 so you have everything now here. And the other file that I provided is the RX 441 that it was used for a different experiment. So it represents another model, so we can open it and check it. Open this one. So in this case we have another model, and it represents a comparison, and okay, you can see here that I'm uploading the identified ARX 441 model, which is a different, and if we run it, and of course also the regressor is different, so it's considering one delay more because the RX is 441. So in this case, I'm considering 4 regressors, and let's see if we have now we have 94, which is slightly, and 95 for the recursive. And if we compare, let's check, we can see that there are some, well, it's not so bad. Also the model of order 4, so you can consider it. So we obtain, so we can consider the delay of order 3 of order 4 when we are going to study the nonlinear model. Okay, with this in mind, the next step is the design. So this can be considered a reference model, linear reference model. Let's try to find the second step, a nonlinear reference model that will be used for the design of the control. And we can examine it in the next movie. Okay, thank you for your attention.